Hello, welcome to the intro video for homework 2, which covers lists and arrays. There's three main chunks to this homework. So the first thing is covering linked lists. And basically you're going to be doing this method called natural runs and also writing tests for the above method. And so that's working with linked lists. Then we have arrays. And so here you're going to be implementing the two methods concatenate and remove, which again work on arrays, and some tests for these two methods. Lastly, there's this really cool part of this homework about image processing, basically. And so the two mandatory methods you have to do are called accumulate vertical and accumulate. And then we have this optional two methods, find vertical seam and find vertical. And while these parts are optional, completing these two methods is what enables you to do like the really cool part of the homework. So I totally recommend it. And the grading scheme is sort of outlined here. This is also in the spec, but just to be super clear, you have to have done, each of these to get full credit. You don't need to like have perfect implementations, right? That's why we say you only need to pass like some of the tests, but we want to see that you put an effort to all parts of the homework. And so this is the grading scheme. We can start by talking about linked lists. So as you already know from lecture, and I think is like lab and discussion, linked lists are these modular lists that are basically a chain where each like link in the chain contains the item as well as the pointer to the next link in the chain, right? And so in this homework, we gave you the class intList, which is a specific linked list implementation that holds integers, which is why it's called intList, right? And so the two main like fields in this intList class are head, which holds an int, and tail, which is a pointer to the next link in the chain, which is just another intList. And so we can imagine this is one intList object where its head has a value of 3 and its tail is pointing to another intList. And this intList is next in the chain. It has 1 and then we have 8. And so in total, this is an intList containing 3, 1, and 8. Notice that the last element has its tail as null. And so in similar vein to the 2D arrays from last week's homework, right, multi-R, we have also given you the class intList list. So this is kind of meta, but basically here, head like holds an intList, not just an int, right? And tail stores a pointer to the next link in the chain, which is another intList list, right? And so here, the values at each item in the intList list is an intList. Or in other words, it's a list of linked lists. Each element in this outer list is just another inner intList, right? And so here we can see like the first inner intList has 3, 6, and 4. And if we go on to the next chain in the intList list, we're going to see this little guy and this little guy, right? And so with these classes in mind, the exercise we're going to have you do is called natural runs. Basically, you're given an input, an int list, and you need to return an intList list with all the subarrays of strictly ascending or increasing lists. And so what do I mean by that? Well, let's take a look at the input. Here we can imagine we only want strictly increasing sublists, right? So we go from 1 to 3, 3 is greater than 1, 3 to 8, 8 is greater than 3, and 8 to 2, but oh, we're no longer increasing on this particular like chain, right? And so we can imagine, okay, this is our first sublist. And then we'll start over because we sort of broke this like increasing chain. So we're starting fresh here. We're starting a new one. And so we go from 2 to 7, we're increasing, but 7 to 5 is a drop. So this is another separate little one. And then we go from 5 and 5 to 3 is a drop. So this one is sort of done, right? And then we go 3, 8, 9, and we reach the end. And so this is another subarray. And so what we've done is we've divided this list sort of into the strictly increasing chunks. And what you're going to return is this intList list with each of these strictly increasing chunks, right? And so within the intList list, you're going to notice that every subarray is strictly increasing, right? We go 1, 3, 8, 2, 7, 5, 3, 8, 9. And so this is why we gave you this intList list class, because that's what you're going to be returning in the natural runs method. And so we don't normally give you skeletons, but to hopefully make this homework a little lighter, we have not given you 1, but 2 skeletons 2 skeletons for the price of 0. And basically the first one is an iterative skeleton and the next one is recursive. You can pick which one you're going to do. You should really only do one. I guess you could do both for practice, but like in what you submit, you should only have one method named natural runs or there will be an error, right? And so we can first sort of talk about the iterative skeleton just to make sure we're all on the same page. So the idea is that this is what you're given and you're going to be putting a lot more code here. Maybe not a lot, but a couple more lines, right? And so the first thing we do is we make this intless list result. And so we can imagine result is pointing to some new intless list that's currently empty, right? And we also make this result pointer that points right here. And we set result.head to be L. So right now, actually, let me move this. Result.pointer is going right here to 1, right? And now you're going to traverse down this. And one thing I want to know is at the end, we're returning result pointer. And this is sort of a common theme we'll see in int lists when we're doing like iterative approaches is that maybe if we remove result further down the line, we're going to need some sort of handle or like grip on the final thing we want to return. So that's what result pointer is for. And so we can imagine this is our setup. And now sort of ignoring the skeleton code, let's just think, what would we have to do to get our solution, right? Well, we'd want 138 to be the first subarray right here, right? So while L.head is greater than L.tail.head, and once we reach this particular element, right? We can imagine we have some pointer right here. We see that we need to sort of start something new, right? We're in this case where my item is, wait, I think we're in this case because, wait, no, we are in this case. If my item is greater than the item, my tails item, right? Or the item after me, then we need to sort of create the next subarray, right? In the result. Right? And so now we can imagine this is the first like subarray. When we start making a new one, so we should also make sure that this guy's head value is pointing to this, right? And we also need to cut off this, make that null. And because we're doing this destructively, we're working with these actual like int list nodes, not making new ones or making copies, right? And so that's why I'm messing with like these actual nodes in my drawing, right? And so we can imagine, okay, well now, so far so good. The first element, right, has the subarray with 138. And then the next one is going to point to this int list with 27, and eventually we're going to have to break it off again, right? But so far so good. And just so we have sort of like a track on where we're at in the result list, right? We're going to move result here. And now we can keep going until we reach the point again where, oh my goodness, my tails item is less than me, right? We're not ascending anymore. And so we need to make another node in our outer int list, right? And the goal here again would be that this one is going to point here. This needs to be null. And now it's almost like we have this little like nice, neat ascending int list here, right? And we'll move result up again. And we repeat this process over and over and over, and eventually we'll reach the end. And so hopefully that made it a little more clear, like what you need to be doing in this iterative skeleton. Remember, every piece of like what I was just saying, has to kind of correspond to some line of code, right? And so hopefully that is helpful to getting a start with the iterative skeleton. Alternatively, if you wanted to use that recursive skeleton, let's go over that. And so we actually give you this really helpful helper method called end of run, right? And so this, if you look at it, basically it's looking for the end of a run, or in other words, like when we've reached the last element where it's strictly ascending, right? And so if we called end of run on this list, we would see that gives us this node, right? Because now we've reached a point where, oh, my tail's head is not greater than my head, right? And so what could we do with this information? Well, we can imagine that somewhere in here, the idea is we are going to want to like use this list, right? And sort of break apart. And so we see that we're going to return a new int list. So let's go ahead and make that. And we know that the head value is L here, right? So that's here. And what we want, ideally, is for the rest to be some other int list that points here. And then this is all broken up into the natural runs too, right? And this L, or the like first one, should be sort of cut off. Or in other words, this should be made null so that it's its isolated own little like sub int list, right? So for the first part, how can we get to this element and make sure its tail is null? Hint, we have a method that we just agreed would get us there, right? To the end of our first run. And so maybe that's helpful. And then the other thing is, well, how do I make the rest of it happen? Do we have some method that we could call that takes an int list and divides it into its natural runs? Well, yeah, that's natural runs, right? This is the recursive leap of faith. We're trusting, oh, I know my method that I'm writing is going to take all this and break it into its proper chunks. So the rest of me should probably just be taking that recursive leap of faith, right? And so this part we can trust is going to be properly divvied up if we make some sort of recursive call here. And that might help you in defining this rest that you will return. And so that is sort of my hints for the recursive skeleton. I would say that if this was not super helpful, if it was confusing, just sit with the code for a while. I'm trying to be vague to not give you like too much away, but if it's too vague and it's just confusing you, just look at the code on your own and do what makes sense to you, right? You can delete the skeletons if you want, you don't have to use them. And with that, we're going to move on to arrays. So the first thing here is catenate. This takes in two int arrays, A and B, and it's going to return an array that's all the elements in A, followed by all the elements of B. So for example, if A was this and B was that, catenate should just return everything in A, followed by everything in B. Hopefully this is not too complicated. As a hint, you can use this method called system.arrayCopy. You should go look at the documentation yourself, right? That's part of becoming a programmer, is learning how to like read documentation for code and learn how to use those methods. So I'll leave it to you to figure out how you can call this. But basically, once you pass in the proper arguments, using this method should make catenate pretty simple. For reference, the SAF solution is, I think, 4 lines. So don't overcomplicate this one. Like, it's not meant to be super complicated or a lot of code. Then we have remove. And so this one just says, given an array A, remove len items starting at start. And so let's go through 2 examples. First, let's say our array A looks like this, right? We want to remove 3 items starting at index 4. And so here, index 4 is going to be right here, right? And we want to remove 3 items starting at that index. And so the result should be 0, 1, 2, 3, 7. The next example, here, we're going to start at index 1. And so remember, we're 0 index, so it's 0, 1, 2, 3, 4, 5, 6, 7, 8. And so this is the starting index that we're going to remove, and we're removing 5 elements here. And so the result that you should return would be 3, 2, 5, 4. Again, you should use system.arrayCopy. And just like catenate, this method is not meant to be super complicated. It's mostly just like working with the array length and figuring out the correct arguments to call this method with. That is everything for arrays. And now we can move on to images, seam carving. This is definitely the bulkiest part of the homework, but it's really, really cool. So to give us some context for what this problem is, let's say I want to make my image less wide, but how can I make my image smaller without losing some information? This is my original image. One thing I could do would be to resize it or rescale it, right? I just take the whole image and I squish it. But the problem with this is that now it's kind of warped, and the tree, looks all skinny. That's not what I wanted. That's not how I had it. And you can imagine if this was like a photo of a person, like they'd look like, like you don't want that. It's warping the image. The other thing we could do is crop it, but now we're kind of losing some information, right? Like now we don't know that there's this lovely little nubbin of the tree sticking out, or that the cloud has a little nubbin, right? We lost all that in the cropped image. And so the last thing we could do is seam carving. And this is really freaking cool. We're taking the image and we're basically cutting out this sort of like irrelevant portion that doesn't have anything too interesting and making the image smaller. And so you can imagine these pixels right here just went away. And now I have both the tree and the cloud fully in the image. I haven't lost any of the information, right? Unlike the cropped one. And I didn't make it look wonky like the resized one. And so this is what seam carving is, and it's really, really cool. And so looking at a sort of different, smaller example, right? One that's only 4 pixels by 6 pixels. We can imagine that in an image, pixels that are different from their neighbors or higher contrast are more important or have higher energy, right? And so the skeleton code already knows how to find the energy for each pixel and put it into a 2D array. And so for this particular example, this is the corresponding energy array. All these ones at the edge are pretty high energy, whereas for these ones in the middle, they're all this sort of like kind of pinky color for the most part. And they're not that different from their neighbor. And so they're a little less important, right? Whereas between these two, like there's this really high contrast. So this pixel definitely has to stay, because if we cut out this whole row, we're losing all the like greens right there, right? Whereas if we cut out, some of these, at the end of the day, the thing next to it was pink anyways. So we're not losing that much. This is the sort of core concept. To go back to the tree example, in case this is like a little like too abstract for you, we can imagine these pixels, right, would have all been pretty low energy. Anything in here, kind of low energy, right? We could have cropped out a whole row of green, low energy, whereas things related to the tree, really high energy, especially these like red apple pixels, right? Those are super high energy, because if we cut out this pixel, we're losing the entire apple, and it's really high contrast from its neighbors. Whereas again, here, no contrast from the neighbors whatsoever. And like this edge pixel, or like these pretty important, like basically things where they look different from their neighbor are going to have high energy. And so if we wanted our picture to be more narrow this way, let's say, we'd need to remove at least 1 pixel from each row. And so to make the image smooth, we should remove pixels along one like contiguous path from top to bottom, right? Rather than just moving, like picking and choosing all over the image, which would almost create this like weird like Swiss cheese, like, I don't know, like random jagged changes. We're going to do it smoothly. And so ideally, we're removing the lowest energy path. And this lowest energy path is our vertical seam. And so in this particular example, right, the one that we showed here, we can imagine that one example of a minimum energy path would be the one with the red pixels highlighted, right? Because we start from the bottom and we're removing all of this. And so once those are gone, we can just sort of shift everything, slide it all in. And now we have this image, which is 1 column skinnier, right? And so we've made our picture more narrow by removing a like seam from top to bottom. And so the question is, how do we find the seam? Well, looking at the case where we wanted to find a vertical seam, right, like the last example, we can go row by row, and for each pixel, figure out the lowest energy or the best possible path to that pixel, right? going from up, like top to bottom. And so for the first row, there's really nothing above it. And so we can imagine it's like final value in the accumulated energy matrix, or the thing we're trying to make is just itself. That's trivial. But now let's look at this row. And so we can imagine if I were trying to get to this like pixel in the accumulated energy matrix, or the pixel at row 1, column 0, right? I could get here either from going to this or this, because we're trying to do a continuous path, right? So my neighbors up above would be these. And if I took those, my total or cumulative energy is going to be the same either way, because these two are the same. And so it's going to be 20,000, right? And for this example, I could come from any of these neighbors, but regardless, the outcome is the same. It's going to be 1075990, right? And so for the first row, just because they were all the same, nothing too crazy so far. But now looking at this particular item is where we have the first really interesting case. So I'm trying to figure out what is the best possible energy I could get for this pixel. Well, the value there is already pretty high, right? High energy. But looking at my neighbors, I could come either from the one right above me or my neighbor here. And which one's going to give me the lower total energy, or what's my minimum possible energy from any path from the top down to me? Well, looking at the sum, it's clear that this number is lower than this one, right? And so it'd be better, or I could get a lower possible energy by coming from here. And so my minimum possible energy is going to be 200 or 2 million something, right? Rather than if I added these and I would have had 3000000, whatever, right? This is better. And so maybe I added that wrong, actually. This should be 2 here, sorry. And so now let's look at the next example, right? I'm trying to figure out what is the best possible value for this one, right? So now I'm looking at row 2, column 2, or wait, sorry, row. If we're 0 indexing, this is row 0, 1, 2, and column 0, 1. Sorry, 2, 1. I think earlier I might have accidentally, no, I was right. Okay, yeah, we're 0 indexing, so this is row 2, column 1. And I'm trying to figure out what's best here. Well, on any path from top to bottom, my options are going to be my neighbors, right? And the best one is the lowest one. And if I add these two together, my total becomes this number, right? And we're going to continue so on and so forth here, right? I take this and I look at the best of these, and I'm going to add the minimum one. And so we'll do this all the way down. And this is the final result. This is the accumulated energy matrix. In other words, we went from top to bottom and tried to figure out for each pixel, what's the lowest possible total energy I could have from some path at the top all the way down to me, right? Now that we have this accumulated energy matrix, we can move on to finding the seam, or finding that best path. And this part is optional. However, this is what lets you do the cool part. So kind of recommend it. Now that we have the accumulated matrix, finding the best path is not too bad, at least conceptually. In code, it can be a little tricky, but the thought is we start from the bottom, find a minimum total energy pixel, and then work up to find the whole path. And so here, starting at the bottom row, we see that there are actually 3 options that are equal, so we can pick any of them. Let's just say I pick, I don't know, this one, right? And then I'm going to look up at my neighbors and figure out, oh, which one did I go here? So I'm working backwards, basically. And I see, oh, it was this one. And from here I go, oh, which neighbor did I come from? Which one was the lowest? It was this one. And from here I go, oh, which of my 3 neighbors did I come from? Oh, it must have been this one, because this is the lowest. And here I look at my next 3 neighbors, this one, this one, this one, and I end up going with this because it's the lowest. And then I'm here and I look at all my neighbors and all of these are equal. So I could pick this one, or I could pick this one, or I could pick this one. But the result is what we saw earlier, right? We remove everything we don't need and we can basically find this seam or all the red pixels. And so if you choose to do the optional find vertical seam method, you would return an array here that has the indices for each row, which column you should remove in the case where you're removing this like vertical thing, right? And so you would return 3, 2, 1, 1, 2, 3, because in row 0, right, you should get rid of column 3. In row 2, you should get, or row 1, you should get rid of column 2, and so on and so forth. And note that this is just finding the vertical seam, just like how earlier we were accumulating from top to bottom. However, you're going to notice this let us cut out a whole column of pictures and make our image like skinnier this way. But if we wanted to, let's say, make it shorter or flatter, then we should have accumulated from left to right, or in other words, like accumulated the energy this way. And our seam, rather than going like that, would have gone somewhere horizontally across the image, right? And so in summary, to do seam carving, first you're going to get all the pixels that are low energy. Our skeleton code already does this. Then you're going to accumulate the energy to get summaries of the low energy paths. And so accumulate vertical specifically finds a path from top to bottom. And you should also implement accumulate, which does an accumulated energy matrix, either vertical or horizontal, depending on the argument passed in. And so if it's vertical, you could probably call accumulate vertical. But what if you want to accumulate horizontally? Do you need to rewrite all the code here? Or could you maybe find some clever way to call accumulate vertical, right? Optionally, once you have that accumulated energy matrix, you can find the seam that should be removed by getting that low energy path. And so find vertical seam finds a seam from top to bottom, and find seam finds any seam either from top to bottom or left to right, depending on the argument passed in. And again, if it's vertical, you can probably call find vertical seam. And so as a hint, for the horizontal cases, look into the idea of a matrix transpose. And this should help you basically make accumulate and find seam really shortly in like a few lines of code without having to recopy everything you did in the vertical versions. This is the entire homework. I'm going to quickly share my screen from my desktop so you guys can see seam carving in action, the program you'll write, just because I think it's really cool. So I'm in my homework 2 directory. Let me make this bigger. Oh my gosh, too big. Okay, I'm in homework 2 directory and I can look at what's here. We see that we have image. And so when I was in image, I will compile everything using make. I already made it, so nothing to be done right now because I already compiled. And then in the homework 2 directory, I can do this command. And so here I see I'm calling the rescaler program. And the argument I'm giving it is one particular example image. You can add your own images to this folder and do it on them. And I'm going to remove 100 columns and 20 rows. So I'm making the image a lot skinnier and a little shorter. Let's see what happens. And so you can see on the left, we have the original image where it's a bunch of people, I don't know, like boogie boarding. And on the right, we have the seam carved image or the small one. And so look what's so freaking cool. Every person and the mountain and the clouds are still in the picture, right? It's just the distance between them where there was nothing going on, right? In this kind of like chunk of the photo is cut out. And for example, these two people are closer together now too, right? Hopefully you can see my mouse, my cursor. But this is like a really cool little program. And if you want, you can call this on different images by replacing this with a different image in the image folder. And you can change the number of columns and rows you want to remove. So I think this is super cool. I hope you think it's cool too. And I hope that you go scene carve all your favorite photos and see what they look like. And it should be epic. Have a great day. Have a great life. Eat something yummy and drink water. Bye.